Yeah.
I'm glad it was so helpful.
All right. No, thank you so much.
Thank you, everyone.
Okay, so the great privilege to have Matt Jacobs from University of California, Santa Barbara. He's now assistant professor at UCSB. So he finished his PhD at University of Michigan, did postdoc at UCLA, and then spent some time as an assistant professor at Purdue University. Now he's in UCSB. So he's an expert in calculus variational technique in PD analysis and machine learning. So now he's going to talk about signed Wasserstein Barycenter problem.
Awesome. Thanks a lot for the nice intro and the invitation to be here. It's always a pleasure. I apologize about the difficulties with the chalk talk. So today I'm going to talk about the signed Wasserstein Barycenter problem. And this is joint work with my postdoc, Bohan Zhu, who's also at UCSB. So I'm going to start just talking about Barycenter problems in general. And then after we get some of the motivation, I'll specialize to the Wasserstein case and tell you guys some of the results about that. Okay, classically, if you look at a Barycenter problem over some metric space, which is the sort of setting that I want to think about, or the general setting that I want to think about. So this is like classical Barycenters. So I have some metric space. X comma B. I have I have like some collection of points, x1 through xk, that all belong to x. And then I'm going to have some weights for these points, right? And I want to sort of find the weighted Barycenter of these points that I've seen. Okay, so we have these points, right? You have these coefficients. Lambda 1 through lambda k, which are the weights of these points. You typically assume that these guys add up to 1. And then what you want to do, right, is you want to find some point like this that I'll call x bar of lambda 1 through lambda k. And this is going to be the argument over the points in my space where I'm trying to find this point x that's close to all of the points in my distance. Okay. And maybe I'll throw a 1/2 over here. Okay, it doesn't have to be the distance squared, right? You could also have just the distance. And in that case, you're finding some sort of generalization of medians, right? This is some generalization of means. But the main thing is that you have some notion of distance and you're trying to find some point that's close to the points that you have. Okay, so what we're doing today is basically taking this problem and getting rid of this condition that the coefficients live in 0, 1. Okay, so right here, these guys are really sort of representing how much you should care about each point. But what we're going to do is we're going to relax this and we're going to allow them to be real valued. Okay, so this is where the signs are going to come in. And right, we can, so we want to generalize to the lambda i's now just being real numbers. But this constraint that they all add up to 1, we are still going to keep that. Obviously, if I change this optimization problem by a constant multiple, that doesn't change the thing that I'm looking for. And also, if basically the negativity dominated this problem rather than positivity dominating this problem, you just won't have solutions at all if your space is unbounded, right? So, keeping this condition is quite natural. Okay. So we want to do this generalization, and what I want to explain now is, basically why. Why do we want to care about this more general version of the problem? And in some sense, I'm going to give you guys two motivations. There are certainly more than these two, but in some sense, both of these two motivations are coming from how do I do vector space things when I don't have a vector space structure? So how do I generalize vector space operations to just like a metric space? Okay, so the original thing that motivated me to look at these problems are things like accelerated gradient descent or higher order accurate schemes for computing gradient flows. So this is descent methods. Slash higher order accurate. Sorry about the squeaking. Oh, that's true. Yeah, maybe that would help. Higher order accurate gradient flow. Approximations. So this was one motivation. And the second motivation that I'll tell you guys about is essentially linear regression when I don't have vector spaces. Okay, so this is sort of like linear regression in quotes. Without vector space. Okay, so let's start with this first thing. If you are familiar at all with things for accelerated gradient descent, things like Nesterov's method, a key idea in all of those methods is some kind of momentum. Okay, so a typical gradient descent method or proximal point method, you look at the point that you're currently at, and you have your function that you're trying to minimize, and from that point, you just try to go somewhere where you're going to have a smaller value of your function, right? I mean, that's basically what these descent methods are doing. And then with things like Nesterov, they saw, okay, you can actually get faster convergence rates if you also pay attention to the direction that you've been going in, right? So if I imagine that I'm sort of doing my gradient descent method and I've generated points xn minus 1 and xn, then of course I know that I've gone from here to here, right? And so I'm going in that direction. And the whole point of these accelerated methods is that I'm going to keep some memory of this direction when I try to do my next update, right? And so the question is, if these are not points in a vector space, right? I've tried to draw an arrow that's connecting them. But of course, if I'm not in a vector space, that just doesn't even make sense, right? And so how do we generalize this notion of sort of continuing in a direction that we've been going in? And so actually the idea, right, is, so let's say like over a Hilbert space, for instance, I can always define the following path. So I can always define x of t to be T xn plus 1 minus T xn minus 1. Okay, when T is between 0 and 1, which is kind of relating back to these coefficients being in 0, 1, I'm sort of interpolating between these 2 points along that line segment, but as I allow T to be larger than 1, or I allow T to be less than 0, then I'm sort of either extrapolating in this direction or extrapolating in that direction. And what these momentum-based methods want you to do is to keep extrapolating in that direction. Okay, so I can always do this on a Hilbert space. Of course, I can do this on any vector space. But at least over a Hilbert space, doing this is equivalent to solving a Barycenter problem. So this is equivalent . This is equivalent to defining x of t to be the argument over this space. Maybe now I'll call this a Hilbert space H. So this is equivalent, right, to doing this. And now this makes sense on a metric space, and I can choose this as my sort of generalized notion of what it should mean to keep extrapolating along this curve. Because I can look at this problem for values of t larger than 1, right? And this tells me which direction I should keep going in. Okay, so I could take this problem now as my definition of momentum in my general metric space, and then start taking things like this and plugging it into those schemes. Okay, so this is sort of the idea of how you would use these problems for accelerated descent methods. This is a particularly simple version because you only have 2 points. But if you want to do these higher accurate gradient flow approximation schemes, then you're going to run into these settings where you actually need to look at things like this, but with more than 2 points. Okay, so, right, gradient flows over a metric space. You have something like x prime of t is going to be some sort of like, basically, I can't really write a gradient here, but you have some idea of like a generalized slope of some energy function, which is going to be related back to the metric in your space. Okay, and it's well known that if you have equations like this, the following gives you a first order accurate . So I will get a first order accurate approximation to equations like this if I do something like xn plus 1 is the argument over my space of my energy plus the distance from where I was before squared, and then I divide by this small time step, okay, which will be the time step for this scheme. So this scheme will essentially have accuracy delta t if I try to approximate this continuous equation that I actually care about. Now, what if I want higher order accuracy in delta t? Again, over a vector space, you would want to think about things like momentum, or you would want to sort of take some curve in your space and come up with a higher order spline approximation to that curve. In some sense, the curve that you build with this sort of method is piecewise linear. And to get higher order accuracy, you want something smoother than piecewise linear. Yeah.
So for XT, in terms of accelerated descent method, are you considering to find xn plus one, which is the next time step, or?
Yeah, so, right, you would take this idea of momentum, just to say like minimizing things like this is how we get momentum. And then you would plug it into your optimization problem. Like basically the proximal point method for minimizing a function would say you minimize the sum of your function and a distance squared term to where you were. And what you're gonna do is basically generalize that proximal point method to add something like this. And you're gonna choose t ultimately to be something larger than 1.
Oh, okay.
And so you wanna stay close to where you were while minimizing your function, but then you're also repulsed from where you were to, the previous step. And this somehow does the same thing as momentum does in Nesterov's method. So right, this is a first order accurate method. But recently there's this paper by my advisor Salim Asadoglu and some of his co-authors. Pretty recent, it was in 23, where they generalized these first order accurate methods to actually essentially an arbitrary order of accuracy. However, you're going to have, instead of a term like this, you're going to have a bunch of distance terms with coefficients that can potentially be negative. So they're sort of higher order accurate schemes look something like this. So you have these sort of weird intersteps, which are indexed by the m's. And you have these coefficients. And yes, you have schemes like this. And of course, there's some rule about when m is 0 that this should relate back to your point xn. And of course, you still have some kind of time step over here that I should put in. Okay, so the point is that in these higher order accurate schemes, those coefficients lambda im, they can be positive or negative. Okay, and so as a first step to even understand how can we solve this optimization problem where you have both an energy and this combination of distance terms, okay, can we even just understand how do I solve problems like this? Because as soon as you have negative coefficients, things get much more complicated. Okay, so this is sort of this first motivation, right, of these more accurate or faster converging gradient methods. Thank you, Andre. I'm sorry to make you have to keep changing the camera angle. Okay, so that's that first motivation. And then after that, I learned about this second technique, which is trying to generalize linear regression when you don't have vector space structure. And this is something that's starting to become more popular in statistics now. So this is sort of a relatively new idea. So what's happening? Well, I have a bunch of observations xi, yi, that belong to some product of spaces like this. Maybe X could be a vector space, but Y in the setting that I want to think about is absolutely not a vector space. Okay, so this guy is not a vector space. And what I want to do is I want to do some analog of linear regression, right? So that I can just construct a sort of linear map from X to Y. Okay, so we want to construct obviously linear has to be in quotes here. A from X to Y. That's going to interpolate this data that I've seen. Right? Now, there's lots of ways to interpolate data, right? I mean, you could just try to throw machine learning at this, right? But for a lot of these problems, you really have very few data points. And so the idea is rather than throw some very powerful method at it, where you don't know what function class you're really building your solutions in, let me just actually build some kind of interpolation in an extremely simple way, right? I mean, basically linear maps are the simplest possible functions that I could come up with. And so isn't the best interpolation, but it has very high interpretability, okay? And so I think having high interpretability when you don't have very many observations is especially important, okay?
What would be kind of a good prototypical example?
Yeah, so like, for instance, like the yi's could be income distributions of a given state, okay? And maybe the xi's are like some data about that state, right? So, right, yi is like the total income distribution of people living in Minnesota. Xi is maybe some other information about the population of Minnesota. Maybe it's also a distribution, right? And then I want to try to understand how these two things should be related to each other. And typically what statisticians would do with a problem like that is they would just take some statistics from these distributions. And then, right, now you've created objects that actually do live in vector spaces. And you can just do regression on the statistics, but then you're losing a lot of information, right? And so maybe like you want to understand this map because you want to come up with policy interventions that are going to help the poorest people in your state. If the statistics that you're working with are the average income of your state, right, you might not be intervening in the right way. So yeah, that's one example, but yeah, I've seen people doing it for like graph value data. And there's all sorts of things that you can try to do. And the idea is that we want to try to do this using basically just metric space structures from these problems. So we're going to do this essentially in 2 steps. So given some input, we want to construct a new point y, which is going to be this linear map, A of x, or linear again, that lives in y. And we're going to do this in 2 steps. So unless people have questions about it, in which case I'll be happy to say more. I'm gonna be vague about what's happening in this first step. And then we'll see that the second step is solving one of these signed Barycenter problems. Okay, so the first step is find the best coefficients lambda 1 through lambda k to represent x in terms of the x y's. Okay, so if you imagined that x had a vector space structure, then what I'd be doing is I'm trying to find coefficients lambda 1 through lambda k such that if I write a point that is the linear combination of those xi's with these coefficients, right, it's the best representation I could get of this point x. Or, you know, it satisfies maybe also best representation with some other sort of like denoising property that you could get from least squares, blah, 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 okay? So I'm going to be vague about how to do this, but there is actually a setup for this that will also give you some of these Barycenter problems. But I want to talk a little bit more about the second step, which is once I have these coefficients, I'm going to try to make my output the analog of the linear combination of the yi's with those coefficients. And so the way that I'm going to do that is I'm going to say, I'm going to choose a of x to be the argument over x so these lambda I x's are the coefficients that I'm finding in this first step. And then what I'm going to do is I'm going to be minimizing, sorry, this should not be the argument over x, it should be the argument over y. I'm minimizing the squared distance. And also throwing it over too. Okay, so once I have these coefficients that represent my x's in terms of the xi's, then I'm going to use those coefficients to try to find y's that are close to the yi's in the same way. Now, why do I say that this is the right way to generalize linear regression? Because if capital Y is a Hilbert space, then this operation is literally doing the linear combination of the yi's with these coordinates. Okay, so if Y is a Hilbert space, then A of x is literally this linear combination. So in a sense, what does solving these problems really do? It generalizes the idea of spans. Okay, so in fact, what you can show is basically the set of points y1 plus span yi minus y1 this space is equal to the minimizers that I can get from this problem as I range these coefficients over all possible real numbers that add up to 1. So this space and this space are equivalent. So this is y such that and again, the lambda i's, or let me just write this as lambda, they belong to all possible vectors I can get in Rk, and then just mod it out by this relation that they add up to 1. So if there's one thing that I would be happy you got out of this talk, it's that solving Barycenter problems where you then allow the coefficients to have signs, this is the generalization of the idea of taking the span of a bunch of vectors. And the one reason that I kind of have to have this offsetting is I haven't, right, I'm saying y is a Hilbert space, but I haven't told you guys what the origin is, right? So now y1 is just like this specialized point that we're treating as the origin, and then everyone else is defined in terms of their difference between themselves and y1. And of course, you know, you would get the same space if you chose any one of the other yi's instead of y1 to do this. And so let me just say one more thing about this. When you restrict your coefficients to lie between 0 and 1, and let me just draw a really simple example with 3 points, what you get is the simplex that is spanned by those 3 points when you range over all of the possible coefficients. When you then allow signed coefficients, right, and you only have this constraint, what you actually get, and I mean, now this won't be interesting because it's just a triangle in the board, but if this was like a triangle in 3D space, what you would get is the plane that that triangle lives in. You would get the whole hyperplane. So technically in this example, I would get the entire wall once I generalize my coefficients. Okay. And so for sure, when you're trying to do these linear regression problems, you do not want to restrict your lambda i's to be non-negative, because that substantially decreases your representation power, right? You're going from only being able to represent a triangle to being able to represent the entire hyperplane that that triangle lives in, at least with 3 points, right? Okay, so these are essentially the motivations, which is just to say that the right way to generalize, or at least one way to generalize these vector space ideas, is to recast them as Barycenter problems with distances.
Can you say again why the sum of lambda I to 1 is?
You don't, okay. So it's important in terms of connecting things back to the variational problem, because the variational problem doesn't see me changing this by a constant factor, right? So if they sum up to C, I will still get the same, I get the same minimizer as long as C is positive. And then it's just a bad optimization problem if they sum up to something negative. Yeah. So yeah, you're totally right that in there's not really a reason that you should have this restriction in the vector space setting, but you're forced to put that restriction for metric spaces. But you're not, I mean, right, you're not losing very much. Yeah, it's at most just a single coefficient. So you're going from RK to RK minus 1.
Is it true if you add a constant to all the lambda i's, it doesn't change?
If you add a constant, it changes, but if you multiply.
You're saying
by it-
multiply, okay,
Yeah.
okay, okay.
I have some
Yeah.
stupid question. So is A you define there is a linear is that a linear map or?
I mean, it's a linear map, right? It's what I want to say is the meaning of a linear map when you don't have a vector space anymore. And so if you had a vector space, then, I mean, provided that you also are choosing these coefficients in a linear way, then it is a linear map. Yeah. Okay, so now you have the motivation. Let me just talk about this problem over the Wasserstein space. And one reason that the Wasserstein space is particularly interesting is that, as I was kind of mentioning when Will was asking about specific examples here, a lot of the times the examples that you get are you have distribution value data, right? You have probability measures. And also, of course, for the first application as well, right? There are lots of gradient flows and optimization problems that you want to solve over the Wasserstein space as well. Okay, so now fine. I'm going to focus on W2 for this talk, but you can look at these problems for more general optimal transport costs. So now I'm going to be given probability measures, mu1 through mu k, that live in the space of probability measures over some Euclidean space with bounded second moment. And what I want to do, and of course I also have my coefficients. Again, these are just going to be real valued and sum up to 1. I want to find some rho star that is in the argmin. Of these squared distances. Okay, so that's the problem we want to solve now. This problem is very well studied when the lambda i's are non-negative. This dates back to 2011 by Agua and Carlier. But things get way more complicated as soon as you allow negative weights. So when all of the weights are non-negative, this thing as an optimization problem is L2 convex. And so that means that if I look at one parameter families like this, then this problem, when the lambda i's are convex, or sorry, when the lambda i's are all non-negative, you'll be convex along these kind of interpolations. As soon as you have a single negative lambda I, you are no longer convex along these kinds of interpolations. And that makes this problem much more difficult to solve, or just study in general. So. Okay, but that is not the only interpolation that we care about over the Wasserstein space, right? These are L2 geodesics, but there are also these other displacement geodesics, right? Or generalized geodesics in the Wasserstein space. And so those kinds of geodesics look something like this. So I take two different maps. So T1 and T0 are going to be maps from RD to itself. And I then use these maps to push forward some measure mu. Okay, and this defines, again, a one parameter family of curves in this space. Okay. So this is displacement convexity. And actually the original problem where all of the lambda i's are non-negative is not convex in this sense. So this is displacement convex. Let's just say displacement / generalized geodesics. And so this problem is not displacement convex. And one very surprising thing, and actually this was proven before, our paper is still not out yet, but this got proven while we were still working on things from a paper of and Sabare and someone whose name I just forgot, so let me give them proper credit, Roni. So this came out just in November. And what they showed is actually if you have one positive coefficient and all of the rest of the coefficients are negative, you actually are displacement convex in this sense. So this is very, right? We already knew this result and we were also surprised by it when we got it. But if, let's just say lambda 1 is positive and lambda I is negative, then the Barycenter problem is displacement convex. And in fact, it's actually one strongly displacement convex. So let me add that in. Along the following particular choice of geodesics. Yeah, just one second. Along the choice of geodesics, where you have to choose the measure associated with the positive coefficient as your baseline. Yeah.
What is T1 and T0?
They're just maps. So all of these T1s and T0s, they're just maps from RD to RD.
They can be arbitrary maps.
I mean, you don't want them to be totally arbitrary. And in fact, you probably want them to be optimal transport maps already. So basically for W2, gradients of convex functions. Yeah. So they had one proof of this. Our proof is a little bit different. And so let me quickly describe it, which maybe this will be the last thing that I say today, since there isn't much time left. And it's actually based on a really, really simple observation that once you know it, it's almost trivial, but I was very surprised about, despite having worked on optimal transport for like the last, I don't know, 7 or 8 years. And you can prove this from the fact that given any measures mu and nu, that belong to this probability space with bounded second moments. If I take a map and I send it to this value, this is a convex function with respect to this map. And so one very bizarre thing about the Wasserstein distance, which I never realized before, is that if you parameterize your measures in this way, actually negative W2 squared is a nicely behaved function, but positive W2 squared is actually horrible. And this is why that's why you actually have this really nice property when all of the weights but one are negative. In general, without the negative sign, these things are bad. But if you have t push forward mu and mu in your second coordinate as well, then these things are nice. And so you choose your reference measure as that first coordinate. And then your first coordinate with the positive coefficient behaves nicely. And for this reason, all of the negative coefficients behave nicely. This literally just follows from essentially completing the square in the definition of, or expanding the square in the definition of this problem. So negative 1/2 W2 B push forward mu comma nu. Because usually this is given as a minimization problem, I have a negative sign, so it's actually going to become a maximization problem. So I'm going to have the soup over, let's see, I'm going to call these maps Z that push this push forward into the thing that I'm supposed to get. And then I should have the negative of 1/2 Z minus X squared. dt push forward mu. If I carry out this push forward and move this map inside, and then I just call S to be Z composed with T, then I can rewrite this problem as the soup over maps S that push mu to mu. And I have negative 1/2 T minus S squared d mu of X. So I expand out this square, I'm going to get a negative 1/2 T squared. And then I'm going to have a term that is linear with respect to T. And so I can write this as plus this supremum over, and rather than say linear, I should really be saying affine. And so this is this for supremum over S push forward mu equals nu of, I'm just going to write maybe A T S, but the point is that ATS is affine with respect to T. And if I take the supremum over a family of affine functions, I get a convex function. And so this is convex. And so when I add back this guy, I kill this thing and I just get a convex function. Okay, we had some theory to cover other combinations of coefficients as well. But in some sense, the other cases where we can guarantee a unique solution are essentially related to this idea where as long as you have one positive coefficient that's pretty strong and your other positive coefficients are relatively close to zero, then you can give criteria on a Barycenter that will guarantee that that thing is a unique solution. But in some sense, those results are that we have are essentially perturbations of this idea. And so the sort of really key thing, which surprised me, is just the fact that negative optimal transport distances are actually nice objects when you think about them in the displacement convex sense. Okay, so I will stop there and thank you for your attention.
Any question?
Yeah,
Yeah, but if you use BB formula, the negative behaves very bad.
if you use what formula?
BB formula, BB dynamic formula.
Oh, if you tried to do Benamou-Brenier.
Yeah, but you get a negative plus a non-smooth stuff.
Yeah, so the way that you parameterize the problem really matters. And so for the negative terms, you really want to parameterize them in this way. But the problem that you have when you have mixed sign terms is like, yeah, if I want to parameterize my row as t push forward mu, then the positive coefficient terms are, these terms are bad when these two are not the same. And so essentially combining, yeah, you have to do some work to combine the various ways of thinking about this problem. So for the positive weight terms, we use more standard ideas, like we don't actually do Benamou-Brenier, but we do like the Kantorovich dual formulation of optimal transport. So that's what you want to do for the positive terms. But for the negative terms, it's better to think about them like this, because basically every other way of thinking about them is bad, kind of. Yeah.
Actually, there's one online too. So.
Oh, okay.
It says, what is the energy for lambda? This was like 20 minutes. Sorry, I missed.
Oh,
What's the energy for lambda?
maybe this was when I was talking about the gradient flow stuff, or
So, yeah.
the energy could be anything. It's just whatever is the right thing for your problem. So that was just meant to be a general stand-in.
I have a curious question. Do you have potential ways to compute these Barycenter problems numerically?
Yeah, so the way that we would try, that we want to do the numerics is essentially to dualize the positive coefficients.
Yeah.
Probably we would dualize the negative ones as well. And then you get these interesting dual problems that are min-maxed, and you can try to just apply min-max optimization algorithms to them. You can also try to do some combined thing where you dualize the positive coefficients, and you try to think about the negative coefficients in this displacement convex. But there's already, like, we originally wanted to write a paper about algorithms to solve this problem, and there was just so much theory happening with the structure of these problems that this paper is just going to be the theory, and we're going to write another paper for algorithms. Yeah.
Looking forward to it.
Yeah.
So if you drop the square in the energy, does this stuff go through still, or is it much more complicated?
Like this idea.
Like if you just do sum of like the actual like not the sum of the squares of this.
Yeah. So there's a way to generalize this sort of convexity property or uniqueness property to arbitrary costs, but it does come down to some property that your costs have. And so at least in like the purely one positive, all the rest negative case, let's see, what should I erase? You want something like this, which is you look at this problem of just taking a single point to So this guy's gonna be positive. Yeah. let me write this. So if you know, and this is a statement purely about what properties this cost has. If you know that for every collection of points, x1 through xk, that every local min of this problem is a global min, then you will get the same sort of, I mean, you can't quite talk about convexity because it's not really the right concept for these other costs anymore, but you would get the same kind of uniqueness statements that you can get from knowing this convexity. Yeah, so like one way to think about generalizing convexity is convexity guarantees that local mins are global mins. And that's kind of the thing that you really need. Yeah.
Maybe I missed it earlier. Is it obvious that the problem has a solution with our negative points? And there's a-
Yeah, I should have said that. So solutions exist because the coefficients add up to 1.
Yeah.
All of the measures are have bounded second moments. And so the only way that a solution could not exist is if for whatever reason it's good to try to send mass out to infinity. And then, right, you try to pass to a limit and you lose mass.
Yeah.
And essentially that can't happen because as you send stuff further and further away, the quadratic part of the distances are what's dominating. And the quadratic part actually doesn't see, as long as you have things with bounded second moments, the quadratic part doesn't see the data. And so the fact that the coefficients add up to 1 means that it just behaves like quadratic.
If they were to add to a negative number, this would.
Yeah, then you would not have existed. Yeah. Yeah.
Would the solution be unique?
We don't know. So in this case, where you have 1 positive, all the rest negative, the convexity implies uniqueness. And then that condition again in the 1 positive, all the rest negative would also imply uniqueness. For these just general combination of weights, what we've proved is if your Barycenter satisfies, or if you have a candidate solution that satisfies certain properties, then it is the optimal solution. But that still doesn't actually, no, sorry. If it satisfies those properties, it's optimal and unique. But we don't know what to do if, we can't guarantee that you can always find something like that. Yeah.
All right, so let's thank the speaker again.
Oh, yeah. Oh, yeah, nice.
Nice to see you.
Yeah, you too.